Um, hey guys, this is Ashish. You're in the third lecture for CVN 9625. Let me know if you can see the screen and hear me, please. Everything good. Excellent. Excellent. Okay. Okay. Just before I get started, some people in the discussion board have been having difficulty in locating the video recordings. So basically, when you get into Blackboard, first of all, you click on Moodle, the link to the lecture or the tutorial recording, okay, or the tutorial. And the screen that opens up is this one that is shown over here, okay, the one that is being shared with you. So essentially, all you have to do is to click on this item, this particular menu. And normally you're in sessions, which is the sessions that you see over here, okay? All you have to do is to go into recordings. And the recordings can be downloaded. So you don't have to just stream them. If you have a bad internet connection or something like that, just download it, okay? And you can watch it later. So just remember this in mind, keep this in mind. All of the recordings, that means the lectures, which is week 1, week 2 lectures, they are sitting over here. And then the week 2 Blackboard recording is sitting over here. And the same will be happening for later weeks. So just keep this in mind. Okay, now I'll take this one back to my regular screen and get started with today's lecture. Okay, so last week I didn't quite finish this climate change presentation, and I wanted to quickly go over this before getting into the next part of the course, which is on design flood estimation. Okay, so I told you the big picture. The big picture is pretty much summed up by the title. If precipitation extremes are increasing, why aren't floods? And IPCC, the International Panel on Climate Change, Intercontinental Panel on Climate Change, it has been always arguing that climate change will increase floods until this paper came out. So this paper came out in 2018, December, and it's one of those fairly high impact, prominent papers. It has been covered a lot by the media and by others. And essentially, it says that precipitation extremes are increasing, but floods are not. So why are precipitation extremes increasing? Well, as I said before, as your temperature increases, the saturated vapor pressure will increase. That follows from that big equation that ES is equal to something EXP T plus something upon T, okay? So that equation, you bump up T by 1 degree centigrade and you will have an increase in ES, okay? And ES represents the maximum moisture the atmosphere can store. So if the atmosphere can store more moisture at higher temperatures, means under extreme conditions, not normal conditions, under extreme conditions, there is more moisture sitting in the atmosphere. And when it comes down, there'll be a lot more. So as a result of that, the extreme rainfall, not normal rainfall, but extreme rainfall will increase. Intensities will go up. But at the same time, as temperature goes up, you have more evaporation. And so your soil moisture depletes down faster. Okay, remember, soil moisture increases to a maximum if there is a lot of rainfall. But when rainfall stops, then the evaporation is the reason why the moisture is decreasing. I mean, this is what you guys are doing in your assignment. Okay, The moisture decreases as you have evaporation. The thing is, evaporation will increase with temperature. Like, you guys are doing your calculations. In your calculations, in your Excel spreadsheet, just increase temperature by 1 degree centigrade, and you'll see that your potential evaporation increases as a result of that. Okay. And what it means is that theta will drop down towards wilting point faster. Now, the issue is your rainfall is increasing, but your theta is decreasing. So which one will win out? If theta wasn't decreasing, the floods would have increased. Okay? If rainfall wasn't increasing, but theta was decreasing, the floods would have decreased. But the issue is both of these impact the sky in opposite ways. Precipitation increases it, soil moisture decreases it. At the end of the day, what we have found using actual data is that the moderate floods, not the very extreme floods, but the moderate flood events are actually decreasing. While the more extreme floods, the ones that, that cause deaths, the ones that we use for our design applications, in small urban catchments, they are increasing. And I'll just show you how we arrive at this conclusion. Okay, logic is we use temperature. Temperature we know is increasing, so we make use of this assumption. And now what we do is we try to quantify the trend in any extreme, could be a flood. And the problem is that it is very unstable. This trend is almost impossible to quantify. So basically, you can't really quantify the trend that easily. So we use a trick. And the trick is that our trend can be expressed as a multiplication of two terms, of term 1 and term 2. Okay? So the second term is positive, and the first term we don't know. But because the second term is positive, all we have to do is to estimate this first term. And this first term is called the scaling, the Clausius-Clapeyron scaling, which equals 7% per degree centigrade, okay, for rainfall extremes and for saturated vapor pressure. Okay, so this is something you need to verify on your own and just do it because it is worthwhile doing it. Okay, this is the reason why you have big rains around the equator and small rains around the poles, because the atmosphere cannot store that much of moisture around the poles. Whereas around the equator, it can store a lot of moisture. So you can have really high intense rainfalls over there. Okay. Okay. So coming back to floods, this particular paper used 5,000 catchments, and these catchments were all free of snow because snow is a messy animal. When temperatures increase, snow melts faster and it has complicated impacts on flooding. But this increase in flooding because of snow melt has got nothing to do with rainfall. We just wanted to focus on rainfall-driven flooding. So we excluded all snow melt originating floods and catchments. And we used 5,000 catchments and 50,000 rain gauges across the world. And what did we do? We estimated these two guys, the scaling for precipitation extremes and for stream flow extremes. Okay, so what is an extreme over here? Extreme over here is usually the top 6 precipitation events each year and the top 6 flow events each year. Okay, so that is how we define these extremes. And basically, cutting a long story short, there is a general increase in precipitation and a decrease in stream flow. Okay, but remember, our events are not like a once in 100-year event. They are the 6 topmost events each year. But if you look at all of these events, lots of events, you look at what temperature was causing them, and you look at the rate of change of the precipitation extreme or the flow extreme with temperature, you find this pattern that the precipitation is increasing roughly at CC, Clausius-Clapeyron, but that the flood are decreasing. Now, this is a pretty important observation, guys. I mean, you have to understand this is something that is quite scary, and I'll tell you why. This is a rough picture of what was presented in the complicated global plot before. Okay, so in this picture, you're having the scaling, which is your del E by del capital T standing for temperature. Okay, this is percentile. So this is basically rare, and over here is frequent. Okay, now what are these different lines? Well, first of all, this line is your precipitation line, which is kind of approaching the 7% CC scaling. Okay, the 7% dotted line is a little above that, and there are good reasons for that because we are averaging across the world. But basically, give or take, the precipitation scaling is supposed to be at the 7% level. What are these three lines? Well, these three lines, this is your flow scaling, okay, for all types of catchments. This is for large catchments, and this guy is for small catchments. Now, you have done the catchment delineation. We have 5,000 catchments over here, so we used, I think it was 1,000 square kilometer as a separator. So anything less than 1,000 was small, anything more than 1,000 was large. It was sort of arbitrary, but basically we had 5,000 catchments and it gave us roughly equal numbers in both categories. So what is this plot telling us? I mean, there's a lot to absorb in this plot, but this is fairly important. There are four key conclusions. So I'll just go through the conclusions one by one, and you see if you agree with them or not. First conclusion. If we consider only the extreme floods, remember this is rare and this is frequent. Okay? So if we consider the really extreme floods, what can be noted about them? Well, the first thing that can be noted is that the flow scaling is increasing and it is kind of approaching the rainfall scaling of 7%. Okay? And this is especially so for smaller catchments. Now remember, we are not considering urban catchments in this analysis, but smaller catchments behave very similar to urban catchments because in small catchments, it is the rain that creates the flood. In large catchments, the rain is important, but the flood is controlled also by the moisture in the catchment. Okay, so small catchments are very much like city catchments, where the rainfall will create a flood. So what it means is urban flooding is going to increase into the future. And this has a pretty serious impact because currently, I think I told you before, 55% of the world is living in cities. And 35% of the world is living in cities, but this number is expected to increase to 55% by 2050 and 80% by 2100. So more and more of the world's population will be concentrated in cities, not our existing cities. Even new cities will come up, but people will tend to live in cities. Why? Well, the most obvious reason is that the farming related practices are already very mechanized, and that will continue to happen. If you go to France or Israel or any of the developed countries which have significant farming operations, it is two people in a family that control a farm having 10,000 cows. That might be acres and acres in terms of size. Okay, So everything is more and more mechanized already, and this will continue to happen. You would not need as many people in the countryside in course of time as we have now. So people will tend to congregate in cities where their infrastructure will be provided. I mean, of course, this is what the projection is. So we don't know what will happen, but this is the pattern for the past many, many years. So this is our first conclusion. Urban flooding will increase. The second conclusion is, if you look at the second box, which is, remember, not very extreme, but not very frequent also. What it shows is that there is a clear difference in the way rainfall is changing compared to how floods are changing. So rainfall is increasing at a greater rate than flow. Okay. And this difference gets smaller and smaller as you get to rarer and rarer events. The important thing is this is positive and this is negative. So that means rainfall is increasing, but flows are actually decreasing. And because they are decreasing, that has a lot of implications. So what it means is a larger rainfall peak will lead to a lower flood peak. Okay. Now these are fairly frequent events. This is the 98, 99 percentile. So it's not very frequent. These are events that can cause damage in a flooding context. But what we are trying to say over here is that even if rainfall increases, you might not see an increase in the stream flow. So that is a problem because that is not what we use as the basis of our flood estimation nowadays. Third point is fairly important. If you look at this box, you can note some very strong things. Discharges are increasing mostly for smaller catchments, and they are decreasing, okay, for the larger catchments. Now, remember, it's the same rain that is happening in small catchments and large catchments. So why are small catchments showing increased floods while large catchments are showing decreased floods? Well, the reason for that is actually quite simple. Floods in small catchments are a function of rain because the catchments cannot store moisture. Okay? The volume of moisture they can store is fairly small. So the moment you have rain, that volume gets filled up and the catchment is wet. So after that, any new rain basically means that it will just become flow. In a large catchment, that is not the case. The large catchments can store massive amounts of moisture. So once you have rainfall in a large catchment, because it can store such a significant amount of moisture, it takes time for that moisture to get full. Now, unfortunately, the large catchments moisture is now more empty because you're having greater evaporation. So the soils are getting drier faster than before. And as a result of that, the large catchments are usually showing smaller moisture. Hence, when the new rain comes along, that new rain first has to wet the soil and then it becomes a flow or a flood. Okay. As a result of that, for large catchments, this one, you are seeing a decrease, whereas for small catchments, you're seeing an increase in the floods. And this is a fairly critical point. Now, when do large catchments matter most? Large catchments matter most when it comes to water supply. Now, your reservoirs, which store the water that we need in our cities to survive, well, these reservoirs can store a certain volume of water. Once you have a very extreme flood, What you do is you open the spillway in the reservoir and you let those floods out. Okay. But what keeps a reservoir full every year is this frequent flood. You need a big flood in a year. If you have one reasonably big flood in a year, not a damage causing flood, just a reasonably big flood in a year, that is enough to fill the dam, and that dam is now ready to supply water to the population for the next year. So this is fairly important. The frequent floods need to be coming because they are important for filling the dam. The large floods are important for filling the dam, but their full volume cannot be stored. Their full volume will have to be let out, because if you try to store it, it might damage the spillway. And if the dam breaks, then of course you have this massive volume of water going downstream. It'll kill a lot of people, have a lot of destruction. So you don't allow for that. You don't allow for the dam to be full to the top and even bigger waters coming in to be stored. You just let them out. You open the spillways and you let them out downstream. What do you rely on? You rely on the moderate floods coming in and filling up the dam. Note this number: frequent floods are reducing 10 to 15% for each degree rise in temperature. Okay, 10 to 15%. That's where you have. This is a scary number. Okay, what this means is that water supplies in our dams is reducing roughly at this rate, 10 to 15% for each degree rise in temperature. Now, this is all not taking into account the demand of water. If you're a farmer and your soil is getting dry, you need more water as irrigation. So your demand is also increasing. So all we were talking about till now was that floods are reducing and it'll have implications on water supply. But it is assuming that the demand is unchanged. But in reality, if your soils are getting dry, the farmers will need more water. And as the farmers need more water, it means the demand will get even more. And as a result, water will be even more difficult to store in the future. This is actually kind of important to understand and appreciate, guys, because I believe this is probably the scariest part of climate change. People have been talking about climate change as, temperatures will increase, and that is a fair point. Temperatures have been increasing, and that has implications. But then, many, many years ago, I gave a talk somewhere in China. I don't remember where. I think it was Beijing or Nanjing, one place, about climate change many, many years ago. And I told the students, the audience, about climate change. And at the end, I had this question. And this young student, he asked me, sir, I understand that temperatures will go up in the future, but what's the big deal about that? Because all I have to do is to buy a new AC and the temperatures will be in control. And he was absolutely spot on. Your energy costs are reducing in the future. As energy costs reduce, things like air conditioning will be less and less expensive. You can control temperatures. You cannot control rainfall and floods. That is the problem. So the biggest problem of climate change is not just the increase in temperature. I believe the biggest problem is this particular point, that your water supply will reduce. As water supply reduces, what options do we have? We don't have very good options. Okay? I mean, the only option that appears possible is desalination. And desalination is very costly and only viable for people who are living near the ocean. near the sea? What happens to all the people who are inland? Okay, so there is a major problem when it comes to water supply, and I believe this problem has been ignored till now. This paper came out in 2018, and I think this issue is actually one of the most critical things about climate change. And, you know, it falls bang in our area, the hydraulics area, because the solutions to this problem have to come from hydrologists. Okay, now, separate study from the United States using nearly 400 catchments, it said something very interesting. It calculated the annual maximum flood and the annual maximum rainfall, okay? And it figured out how many times does the annual maximum rain create an annual maximum flood? What is the probability of that? And it basically said that if you have an annual maximum rain in these 390 catchments, 36% of the time, that rain will become the annual maximum flood. Okay, the remaining 64% of the time, it might be the second annual maximum rain or the third annual maximum rain or some other rain that creates the annual maximum flood. Now, why is this important? The reason this is important is because this number changes to 62% when the catchments are wet, and it changes to 13% when the catchments are dry. So this is all based on data, and this is annual maximum floods, not the top 6 floods or top 6 storms in the year that I have used in that paper that we showed before. Okay. So what it is saying is the annual maximum flood occurs from the annual maximum rain on average 36% of the time. This 36% becomes 62% if the annual maximum rain is falling on a wet catchment, and it becomes 13% if it is falling on a dry catchment. So what will happen in the future? Well, in the future, as temperatures go up, these wet conditions will become fewer. Okay, these dry conditions will become more. So you will have more of the time this type of event, and less of the time wet conditions prevailing, and more of the time dry conditions prevailing. So on average, this 36% will actually become even less than that. And this is a very brute force, very easy to understand message based all on data. There is no model being used here. This is hard data collected by hydrologic measuring agencies from across the world. The data is telling you that your floods are reducing, even though annual maximum rainfalls are actually increasing. Okay, so just to wrap it up, what do we do about this? We are engineers. We can't just complain that this is happening and not really provide a solution. So, well, if you think this thing through, and this is a open point because solutions are not straightforward here. The first option that the world is currently following is waiting for greenhouse gas concentrations to reduce. Okay. The trouble with this option is that people have calculated that the probability of containing warming below 2 degrees centigrade, which is known as the tipping point. Okay, so warming is about 0.8 degrees centigrade till now. They say 2 degrees centigrade is a tipping point. If it crosses 2 degrees centigrade, we have very serious problems. Very serious problems, meaning the the frozen soils up in the north, northern China, Mongolia, Canada, Russia, they will start releasing methane. It might change circulation patterns, ocean circulation patterns. The warm countries in Europe might actually start freezing. So basically, all types of chaotic things will happen. And this is not talking about uh, more tangible or visible things like impacts on plants and biology. Okay, so polar bears, no chance under these type of uh, changes. The chances of containing warming below the tipping point is 5%. Okay, and the chances of keeping it below 1.5 degrees is 1%. So very little chance that you will be able to keep warming below the tipping point by the year 2100. Whatever you do, very little chance. Okay, so waiting for greenhouse gas concentrations to reduce is not really a wise option. There is a second option, which is kind of what people are doing, although not officially. They are doing it unofficially because each water authority is taking, matters in their own hands and trying to act on this issue. So what are they doing? Well, they are looking at how did they handle water insecurity before. So in old times, when you have water insecurity like this, you have a drought. Well, what do? You build a dam. So that is one solution that the world is looking at. Or you build a desalination plant. That's the second option that the world is looking at. Or you try some diversion projects. So this is an example of the south-north water diversion project in China. And it is taking the water from the Yangtze and essentially sending it up in the north. That's the idea. Okay. And the reason behind it by the Chinese government is that the south of China is fairly highly populated and it is fairly industrialized. The north of China is fairly dry. So essentially, you can't really farm over there because of lack of water. So the population in the south, which is growing and growing and growing, has to be fed somehow. And they're saying that, hey, as temperatures, as long as we can create more water up in the north, maybe we can use that as the area to cultivate the crops so as to feed the south of China. This is one example of a water diversion project. Similar projects have been considered elsewhere in the world, and people are thinking seriously about these type of things. I mean, the Chinese have to be credited that they have actually acted on this. So this South-North project is nearly there. They have completed 2 or 3 stages of that, and they are in the last stages of that. And all of this has been done with, the development in China in mind, but climate change also in mind. Okay, second type of water insecurity we have is flooding. Now, this is a picture of Venice. So Venice is getting flooded, very often nowadays. So water levels come up to this is called the St. Mark Piazza, I think. That is the thing that you see over here. But it is normally full of water, which was not the case before. Now, how have people dealt with that? These are examples of dikes, okay, from the Netherlands. Netherlands is a very interesting country. 50% of the Netherlands is underwater, under the sea level. But what they have done is they have put these type of dikes. The ocean level is higher, okay? Ocean level is higher. and the the inland level is lower. And what they do is they have pumping stations that pump water from here to here because the river water has to go into the ocean at the end of the day. So what do? They pump the river water at the end of the river into the ocean. This is how the Netherlands has been doing things for many, many years. And this is another example of how flood-related water insecurity can be addressed through engineering. This is another example. This is the Thames in England, and the Thames is impacted by tidal influxes of water. And basically, they have these gates that kind of do the same thing as the dike. It builds a wall, and it doesn't allow that water to go in. It only opens that dikes up once the danger situation is kind of gone. One other example, this is about flooding. Well, another way of dealing with flooding is, uh, you store that flood water somehow. So this example over here is actually from Tokyo. After the Second World War, Tokyo was a rubble, and they had to rebuild the entire city. But before the Second World War, they used to notice that every year Tokyo gets flooded because of tidal influx of water. So what did they do? Under the city of Tokyo, you find these big, huge reservoirs. These reservoirs are just filled up with water every time a big tidal influx comes in. And then once the tide goes out, once there is no danger, a pump switches on and the pump will transfer the water back into the river. So this is what keeps on happening. You have not had floods in Tokyo for the last 20, 30 years. Before 1945, floods used to occur every year in Tokyo. The same type of underground reservoirs are also present in mostly in very rich countries in rich cities. Zurich is an example. Zurich has something like this. Many of the richer countries, they have invested in creating these massive underground vaults or reservoirs where the water is stored. And after the reservoir is filled or the flood has gone, you switch on the pump and release the water out. So this is how basically people have addressed flooding. I mean, it's not possible to think about these options everywhere, but in some places it is possible. One other example that is being tried out is called WSUD, Water Sensitive Urban Design. We have a good group over here that specializes in water sensitive urban design. You might want to check out the name of the professor is Anna Deletic, and she has done some excellent work in this space. But basically, water sensitive urban design, the idea behind it is small catchments cannot store a lot of water. I told you that thing before. Well, the way they increase the storage for small catchments is by creating cities that are a little bit like sponges. So they have wetlands or they have green spaces, not enough covered areas. And as a result of these wetlands and green spaces, can't store the water that might result in a extreme flood, but in a common flood, a flood that occurs, say, 3 or 4 times every year. Probably that is enough to make a difference. So basically, you have created these patches of green vegetation or wetlands, sensitively designed the cities around them so that these patches will reduce the chances of the non-extreme floods. Extreme floods, these things can't help. Okay, so if there is a flood that might cause, death and destruction, spawn cities are of no use. But the floods that might stop traffic, okay, where water comes up to about 1 foot above the road and you have to stop traffic. Cars can't move. Those type of floods can be mitigated to quite an extent using these type of options. So any new cities that are being developed, especially in China, because China is coming up with a lot of new cities. So essentially, China is trying to diversify its population so it doesn't congregate in the existing massive cities of Shanghai and Beijing and Nanjing and all of these places, but they're coming up with smaller cities. And these small cities are also big by Australian standards, but they are small by Chinese standards. These new cities, the smaller cities, they are legislating the need to have any new developments be associated with these type of sponge areas, okay, wetland or green type of areas. So this is all part of water sensitive urban design, and this is one other option. This is not a fix to all of our flooding problems, but it is one possible thing that could be done. Okay. Now, I have a question from Danny who's asking, how do we transport this water? So I think the transportation part, if we look at these reservoirs, or if we look at the dikes, or we look at these diversion type of structures, transportation is not by gravity. It is against gravity. And this is where the engineering challenge comes along. So you have to have some type of pumping so as to pull water up to a level from which it can go by gravity. That is how you transport the water. Pumping is needed. Without pumping, you can't do it. But you know, the thing about the pumping is um, I'll tell you another story, related story. 50 years ago, our groundwater levels were pretty much the same year after year after year. Okay, nowadays they have gone down by about 30 meters in the Indian subcontinent and in southern China. Okay, why? The reason they have gone down is two reasons. People need water, but they always needed water. People need water, but the demand for water was always high. The second reason is very important. Electricity is cheap. Electricity will get cheaper and cheaper and cheaper as time goes by. So essentially, this whole issue of pumping to create gravity flow, in the case of China or in the case of those storage structures that I mentioned in Tokyo and Zurich, they will require electricity, but that electricity is not inconceivable. Um, they are considering similar type of a diversion scheme for Australia to get some water, possibly from the north into the southern drier states. And again, the energy options they are thinking over there are pretty clever. They are thinking about some type of solar related energy with some energy storage that can be used to create that big pumping push up in the north so that you can have the water come down using gravity for the remainder of the path. In the case of the Chinese system, I might be wrong, but there are pumping stations in two locations and fairly big pumping stations. The rest of it is pretty much gravity flow. So that is the loose way how they would be, doing these type of operations. And look, you folks are engineers. You would know these are the biggest projects in the world. I mean, the biggest project in the world all time would be possibly the new dam that is coming up on the Nile in I think it is Sudan or Ethiopia, but it is upstream of Egypt, and it is something that the whole world is scared about. because it is upstream of Egypt. That is a dam that is bigger than the Three Gorges Dam in China, which was the biggest project, engineering project before. Okay. And I guess probably an equivalent big project is this North-South scheme. The North-South scheme is massively expensive. It's about, if I remember correctly, it was costed at about 40 billion US dollars or something like that, which doesn't seem that big in the whole scheme of things for a massive country, but it is a significant amount of money. So basically, these projects, I believe, will be happening more so course of time, and you as engineers need to study them and keep an eye out for them, because this will change, engineering practices and companies and ways of working in the years to come. Okay. So this is about water-sensitive urban design. I just have a general argument that, in addition to thinking about engineering option, it is also important to be honest about the risk, which is something we have not been till now. And part of the reason we have not been honest is because of politics. I mean, you look at the type of information that comes in from one side of the political spectrum, who will always say that they don't believe in climate change. Because if they start believing in climate change, they have to do something about it. And the doing part is what they are not comfortable about, because it involves reducing emissions. And reducing emissions means loss of jobs, changing of industries, etc., etc., etc. So basically, their political base would not allow them to proceed down that path. And this is not just in Australia or in America. America, it is very prominent and it's very clear, but it is literally the case everywhere in the world. I mean, unfortunately, our political system is such that there are two sides in the political spectrum. And whenever you have two sides, they will take opposing views. And one of the views is usually to deny that climate change occurs, and the other one is to embrace that climate change occurs. And I guess this division is too far for the common person who's right in the middle to be convinced about the need for change, which is part of the problem. So if we are honest in our assessment of the issues, of the risks, then that could be a big factor in any actions that are taken. Because at the end of the day, these politicians are simply our representatives. If the people want something, the politicians will make sure that happens. The people are not totally convinced about what needs to happen, and that is part of the problem. But it's a circular argument, because politicians often get to the media, and that influences our thinking and mindset. Bottom line, this is what I keep saying. We need to think about re-engineering. This is the way to solve this mess before it gets way too costly. Okay, so this was my presentation on the flooding stuff that I wanted to give you guys last week, but I couldn't complete. If you have any questions on this, it might be good to jot them out now, because now what we do is we will get into the actual estimation of the design flood. So the estimation of the design flood is a more engineering concept, where we will be looking at the design rainfall and how it gets converted to a design flood. So if you have any questions, think them through, put them in the chat over here, and I'll come back to it as we go ahead with this lecture. Okay? Okay, so now let me go to this week's slideshow. So I probably said in the first week, if you're a hydrologist, you have two bread and butter problems. The first one is design flood estimation. This design flood estimation is the basis for building anything anywhere in the world. So if you're buying a house, you have to know what is the plinth level of that house. That plinth level needs to be safe from a certain design flood. You will estimate what is the depth of say a 20-year or a 100-year design flood, and I will discuss what this 20 or 100 means as I go along, and then basically decide that this plinth level is okay or not. This is for your house. If you're building a bridge, obviously that is very important. You're building a nuclear power plant, very, very important. Okay, Chernobyl is argued to be a disaster that was partly because design flood estimation was not updated. So essentially, they had a failure which was not supposed to happen because they were not expecting those type of conditions to occur. Many of the horrible engineering failures in the world are related to design flood estimation, where people built something, but the chances of a flood occurring were too high. And of course, chances will always exist, but if the chances are too high, then that causes failure. So this is part one of engineering practice in hydrology, design flood estimation. The second bread and butter problem for hydrologists is water supply. And these two are slightly different in the sense the approaches behind them are slightly different. Design flood estimation is just about the instantaneous biggest flood that can occur. Okay? And water supply is about a year-long water that you need to be supplying to your farmers. Unfortunately, both of them are changing. So I told you that city floods are increasing, more or less. Urban flooding is going to increase into the future. And I told you water supply risk of failure, that means risk of shortages in water supply, is decreasing. Now, if you're in South America where you have, 2,000 millimeters of rainfall and lots of flow with a very small population, I mean, not a very big population at least. So water supply is not an issue over there. If you're in Darwin, where you have lots of rainfall and a fairly small population, water supply is not an issue. But if you're in Adelaide, or if you're in Sydney, water supply is very tricky. It's a very important factor. Okay, if you're in China with a big population, an increasing population that is concentrated in the southern hotter parts, okay, water supply is again a problem. So basically, depending on where you are, water supply is likely to worsen with climate change, and flooding is likely to worsen with climate change in cities where most of us will be living by the year 2100. So there is no positive thing about climate change. I mean, it's not doing anything that is positive. It is basically a horrible mess from both the two angles that hydrologists are needed for. Okay, flood estimation and water supply, and this is important to understand. Okay, so our aim in this course is to estimate something known as a design flood. Okay, and this design flood would normally be written something like QY, or say Q100 or Q50, okay, which is a flood that occurs on average once in 50 years. Okay, not occurs on average, is equaled or exceeded on average once in 50 years. So this is a 50-year design flood. If you want to increase your safety from flooding, you would design your structures for a 100-year design flood. Okay, if you want to take more risks, you will design them with a 10-year design flood. So the risk you're happy to take in the structure being flooded is designated by this guy called Y. And this Y guy is known as the average recurrence interval or the annual exceedance probability. Okay, I'll come back to these terms again. ARI or AEP. So basically the ARI or AEP, they are not the same things, but they are related. They are interchangeable. And this kind of designates this Y thing. This Y thing is the risk that you are designing for in estimating that flood value. But the issue is that this flood QY is some function of what? It is a function of IY, where this is the design rainfall. Okay, so just like you have a flood, you have a flood that can occur with a probability of, once in Y years. Similarly, you have a rainfall that can occur with a probability of 1 in Y years. So just like you can have a design flood, you can have a design storm or a design rainfall. And it is these design rainfalls that are used to estimate the design flood. Now, this design rainfall is a bit tricky because this design rain could occur in 1 hour or it could occur in 1 day. So with a design rainfall, you can't just think about design rainfall. You have to also think about the duration. Okay, of the design storm. And when you put it all together, then what are you having? You're having intensity, okay, which is your I, frequency, which is the risk, okay, which is your Y, duration, which is your D over here. IFD relationships are the basis of specifying the design storm, that is the needed necessary input to design flood estimation. And this is the basis for design flood estimation, not just in Australia, across the world. So IFD relationships are there for literally all parts of the world. And these are what are used for estimating the design flood. Now, some places they might be quite accurate and very well specified. Some places they might be a bit fuzzy because observations might not be that many. The IFD relationship is there anywhere in the world. In Australia, this IFD stuff and design flood stuff is actually specified in a document called ARNR, the Australian Rainfall and Runoff. Okay, and this Australian rainfall and runoff is like a Bible for the flood estimation. All consultants, all hydrologists use this as the way of estimating the design flood. Okay, if you go to America, it's a different document. It's called the NOAA Atlas 14. That gives you the intensity, frequency, duration relationships. If you go to Europe, it'll be a different document. But at the end of the day, all of them are trying to have a basis for specifying the IFD from which the design floods can be estimated. Okay, so this is just a sort of a summary statement of what is involved with design flood estimation. Okay, I have a comment. I'll just read it out. It's a comment from Miguel, and the comment is that even if a region receives a lot of rainfall, such as Darwin, approximately 1600 millimeters, it can still have water scarcity. Okay, if aquifers cannot properly recharge and we cannot store this rainfall properly, that is very true. So so Darwin is one example, the 1600 millimeters. And I can give you many other examples. Other example would be Tasmania, the wettest state in Australia. One side of Tasmania is actually very dry with rainfall of about 400 millimeters. So other side is a lot of rainfall. So even in that other side, or in the case of Darwin, you can have water scarcity if, you know, if firstly the demand for water is a lot, which could be demand by humans or it could be demand by the environment. Okay. Or secondly, if your livelihoods have adapted to expecting a certain amount of rain, but if you have a decrease in that rainfall, then you have to adjust that whole way of living, and that causes a lot of water scarcity and issues. So specifically, what Miguel is saying is that if you cannot recharge your aquifers, if you cannot recharge your aquifers from the 1600 millimeters, then it will have implications elsewhere. It will have implications in other regions because the aquifers stretch on for significant, lengths of the country, and the water is pumped out where that particular water might have actually fallen in as rainfall in a place like Darwin, but it might be getting used much lower, much more downstream. So that is one example. Another example is the state of Sierra in Brazil, where you have this massive hydroelectric system of reservoirs. And again, the same thing, Brazil is one of the wettest countries in the world, but this particular state is not that wet, and it has a water shortage issue. And this water is not like universally short. Some years it is pretty high. So averages can be deceptive. You can have very high rainfall in certain years, but in certain years, significant reduction in rainfall. And when you have the significant reduction, then the water scarcity becomes an even more acute issue. We are actually having a paper come out in the next few months or so, and you'll probably hear about it, which is looking at recharge of the subsurface reservoirs across the world. Recharge is measured using a satellite, which is called the GRACE satellite. And this GRACE satellite is quite cool. It's actually two satellites that are at a certain distance, and they spin around the world's, above the Earth's surface. But basically, when they come above land, the gravitational pull of this satellite is very different than when they come above water. So as a result of that, this particular distance you have, it contracts and expands depending on how much gravitational pull the Earth below them exerts onto them. And they are able to estimate something called the terrestrial water storage or recharge. Okay, so this is the terrestrial water, which means all the snow, all the soil moisture, all the aquifers, everything all stored up. And basically what we did in this paper that has not been published yet, but we tried to quantify, is this terrestrial water recharge changing with time? And the results are quite clear that with increases in temperature, the recharge is reducing. And it has having implications in terms of vision, in terms of a lot of other things. So essentially, there are much bigger issues than just the increase in floods or reduction in water supply that I've talked about. the issue of climate change has implications in ways that we don't really know till now. We are still guessing. Only once it happens will we really understand and appreciate the extent of the damage that has been caused. Okay. I mentioned that design flood estimation is QY, okay? And this Y thing is called the ARI or AEP. And I mentioned the ARI stands for the average recurrence interval, okay? Example, 100 years, okay? AEP stands for the annual exceedance probability, okay? Example, 1% flood, or AEP is equal to 0.01, or ARI is equal to 1 upon 0.01 is equal to 100 years. Okay, so this ARI and AEP are inversely related. ARI is equal to 1 upon AEP. So basically, if you're given the AEP, you know the ARI. If you're given the ARI, you know the AEP. You should be clear about that. Okay, like you should roughly know that 100-year flood is worse than a 50-year flood, because a 100-year flood can be equal or exceeded once in 100 years. So it'll be much worse, much higher levels. 50-year flood can be equal or exceeded once in 50 years. A 1-year flood is the flood that gets equal and exceeded roughly every year. Okay. There can be a 6-month flood. 6-month flood is equal and exceeded every 6 months. So depending on the rarity of the flood, you need to use the flood estimate for different types of applications. What does that mean? That means if you're trying to design a freeway, okay, you will use a 100-year flood as the basis of the design. So basically, the flood should only exceed the road driving level of the freeway maybe once in 100 years. Okay, I mean, I'm just making the once in 100 years up over here because certain segments of freeways are actually designed to flood once in 20 years also, especially if they are not subject to a lot of traffic. But the busy sections of the freeway where you don't want any disruption, you would design them to be flooded once in 100 years. Now, if it gets flooded, it's not the end of the world. The flood will probably clear off in a day or so, and the traffic will be back to normal. Okay, but if you're after a dam spillway, this will be designed for a 10,000-year flood. Okay, why? If Warragamba Dam breaks, if the spillway develops a crack or it spills water, okay, you lose roughly 500,000 people in Sydney. So dam spillways you can't allow to be flooded. You have to ensure that they are designed such that the chances of flooding are absolutely minuscule. Now, you can never eliminate risk completely. Okay, risk is always present in the world, but you can control the level of risk that you want to live with depending on the implications of failure. So typically, if it is a small minor country road going up in the middle of nowhere, used once a week by somebody to take their tractor across or whatever it is, you don't care if it gets flooded twice a year. So you'll probably design it accordingly. But if it is a freeway, you don't want it flooded twice a year. You'll design it such that it does not get flooded with that level of frequency. Okay. So often the risk that you take is a function of the cost of failure. Okay. How costly is the failure? Failure meaning in this case a flood. Okay. If the cost is not too high, you go with a lower risk because that's a cheaper option. Okay, I mean, designing for a 100,000-year spillway is probably many millions of dollars more expensive compared to designing for a 100-year spillway. Okay, so basically, one has to think about the balance of risk to take versus the cost that is involved versus the benefits of adopting that particular risk. That's an important thing to understand. All of this design flood estimation is a little bit about cost benefit analysis, and you tend to take risks that are okay. Who decides this okay? Normally, it is flood estimation guidelines. They are the ones that specify risk to take. Okay. In the case of your house, it might be a local council. But typically it is flood estimation guidelines. So there will be separate guidelines for the roads people. There might be separate guidelines for, say, nuclear power plants. There might be separate guidelines for councils. There might be separate guidelines for other type of water structures that one needs to protect against the impacts of flood. So this is just a sort of a summary of what we are getting into now. But I think this summary is kind of important because what I'm going to cover is a lot of detail. And this detail is not that difficult to understand once you appreciate this summary. Okay. Please use this opportunity to send me questions, send me comments over here. If you want clarifications on any of this stuff, okay, please ask me questions because it makes it more interesting to have some kind of a discussion that and it makes it easier for you to understand or relate to the issues being discussed. Okay, so what are we covering? We are discussing IFDs. Okay, how to construct IFDs, how to use IFDs, and then design storms, which is IFDs plus temporal patterns. Okay, because IFD is simply going to give you an intensity, a design storm intensity, but that design storm intensity is a constant for your duration. If your duration is, say, 10 hours, it'll be one constant value of rainfall for all 10 hours. That doesn't quite make sense. That's not how rainfall occurs. So a temporal pattern gives it a temporal structure. It changes the rainfall in the first hour, second hour, third hour, etc., all the way across to the 10 hours, such that the average intensity is the same as the design intensity for a 10-hour duration that you started off with. So these are the two things that we are covering in the remaining slides. Okay. So these are developed by the Australian Bureau of Meteorology, and their most recent edition is ARR 2016. Remember, ARR stands for the Australian Rainfall and Runoff. Okay, and this Australian Rainfall and Runoff has basically been developed 4 times. This is the 4th edition of Australian Rainfall Runoff that we have. The first 3 editions were paper-based. There were lots of big maps and documents that had to be kept in all engineering consulting offices that would follow the procedures. Nowadays, it is actually available over the internet, and it's a very good document. It's a very well written and well designed document because it has incorporated the best advice from academia, from government, and from the consulting industry. There are people from all branches of the profession that have contributed, and this is the first version that explicitly provides guidance about climate change impacts. Okay? I mean, this first national design guideline document anywhere in the world that provides guidance about climate change impacts, which is a really cool thing, which is a very politically scary thing to do, but still the document is brave enough to provide some type of advice about the climate change impacts. Okay. So I've already mentioned what is a design storm. A design storm is basically something that is equaled or exceeded once in Y years. Okay? In the case of rainfall for a given duration D. So it's not a real storm. This is something that is important to understand. It is not a real storm. It is a hypothetical storm, but that storm on average can be expected to be equal or exceeded once in Y years. And for the case of rainfall, the storm needs to be specified for a duration. Okay, for the case of floods, duration is unimportant. You're just looking at the biggest flood. But for the case of rainfall, the duration is important. So basically, a design storm is specific to a given duration as well as a given risk. So basically, using this design storm, we estimate QY, okay, which is our design flood. And this QY is the basis for finding out the height of this bridge, okay, the size of these canals or solid structures, the length of the spillway, the carrying capacity of the spillway, and this is the most normal use, which is simply the pipe that just, that is just releasing storm water into an open area. So stored storm water, if it has to be released into a floodway or a river or wherever you have to go, the size of this pipe is something that you would design based on design flood estimation. What will happen if the pipe has a smaller diameter than it should have? Well, what will happen is you'll have flooding on this side. These houses will get flooded. Okay, you don't want that. So you have to have the pipe of the right diameter. Somebody might say, hey, why don't we just increase the pipe to twice the diameter? That is possible, but it can be very costly if especially your pipe has to run for significant lengths, over that countryside. So basically finding the right pipe diameter that is not too costly, not creating excessive risk is important, and that is all coming from this design flood estimation procedure. This is how you understand the design flood estimation idea. Okay, so this is a river that you're seeing over here. you can see these flood banks. This is the normal width of the river. You will see some dry patches that are very wet. The soil color is usually different. That will be a typical extent of a 2-year flood. Vegetation will normally start growing after the 50-year flood line. This depends, of course, from place to place and depends on the type of vegetation as well. But typically, when you have a watermark until which there is no vegetation, that watermark will typically be less than 50 years. After 50 years, you'll start having permanent vegetation in that area. Okay, so this is what we are talking about. We are saying that in certain cases, if you're putting a bridge across this particular point, that bridge needs to be anchored far enough such that it can withstand a 100-year flood. That is what we are trying to do. We are trying to estimate the 100-year flood so as to find the plinth level of the bridge. How do we design its columns, etc., such that the bridge is not impacted by flooding. Okay. Now, how can the bridge be impacted by flooding? Well, what happens is you have this big flood. The flood level might increase and it might cover the bridge. And then after a few hours, the water levels will come down. The bridge would still be there, you would think. But you haven't thought that if the flood levels go so high, they would knock down trees from here. And these trees will start coming down. So it is debris, tree debris, car debris, house debris that will actually bump into the bridge, and that is what is most likely to cause structural failure. So it is not just the flood level, but the other things that are associated with the flood that can be responsible for these type of failures. Okay. Okay. Now, ideally, if you want to estimate the 100-year flood, all you have to do is to just take the last 100 years of flood data and see which is the highest flood that you have on record. Not a bad idea. The only trouble is that that is not very practical because sometimes there is no flood data, okay? Sometimes the catchment has changed or the climate has changed, okay? Like in the case of Sydney, if you look at the oldest pictures of Sydney, looking up from the harbor towards what is now the central station, you can search it up. You will come across a building called Cleveland House, okay, which is on Cleveland Street, not too far from Central Station. Now, this Cleveland House was the only building that you could see in the really old pictures of Sydney. And this is bang next to Central Station. It is not even visible now. It is surrounded by skyscrapers all over the place. So basically, development, urban development has changed everything. The design flood that should have been used to construct, say, the stormwater structures for around the Cleveland House are completely invalid now compared to what they were before. It's all because of urban development. So essentially, this urban development is a part of life. And the second thing is climate change. We have just discussed that urban floods are likely to increase because of climate change. So essentially, flood data alone is not sufficient. What do you do in such a case? Okay, you use rainfall or IFDs. Okay, luckily we have lots of rainfall data because flood data is a bit of a pain to measure. I mentioned in the lecture, I think last week or the week before that, measuring floods involves taking a board and cutting the cross section into sections estimating velocity, and then figuring out the overall discharge. It is not simple. It takes effort, it's costly. Rainfall, very easy to measure. So we normally use rainfall. Rainfall data is available literally all over the world. So basically, what we do, our aim is to estimate the flood, QY, okay? But the way we go about doing flood estimation is using actual data, okay? An approach that is known as flood frequency analysis, using nearby flood data, an approach that is known as regional flood frequency analysis. So actual flood data. But the most common approach is using IFTs. Okay. So with this, I'll just pause for some time. Okay. Give me a 10-minute break, and then we get back to the whole thing. But these IFTs are the basis for almost all design flood estimation in cities, and especially for future developments. Future developments meaning, you might have open space right now, but somebody might have bought it and they want to convert that area to a parking lot. So parking lot is still not there. It's going to happen. Now, you are supposed to put a pipe under the parking lot to make sure that your, pretty Lamborghinis and Maseratis that are parked over there do not get flooded and into the river. So how do you design? What should be the size of that pipe? This is all in the future. Development hasn't happened. What you would do is you would often estimate the flood using actual data if it is possible, but because here you're having a development situation, you have to project what the flood will change to because of the development. And for that, often the design storm would be needed. I have a question over there by Jonah. Regional flood frequency is using actual data as well, but for nearby. That's correct. So I'll get into this with more detail later. It's a bit tricky, but say ideal situation is this guy, flood frequency analysis, which means you have flood data at that location, and that location has not changed. It is not urbanized too much. So that is the ideal situation, okay? But real flood data is very rarely available. So if real flood data is not available, what you do is you take flood data from anywhere in that region. So you draw a circle around that region, and you take some data, flood data, from all the rivers, tributaries that you have over there. Argument is that all of these rivers and tributaries would have been fed by similar type of rainfall events. So when you would see a flood over there, it would be part of the same rain system that might create a flood at your location, which doesn't have flood data. So basically, you take data for all the nearby locations. But of course, the catchment size changes the magnitude of the flood. If you have a huge catchment, the flood will be massive because the rain is now falling over a bigger area. Whereas for a small catchment, the flood would be small. So you then account for changes in the catchment attributes and other attributes. And once you do all of this, you can develop a regional flood frequency analysis approach, which is using flood data, not rainfall data. Okay. But this is our second preferred option, regional flood frequency analysis. But the reality is that if you have urban, then you don't have a choice. In urban settings, any old flood data is not representative of the floods you're having now, because you're having constant changes around the neighborhood. Okay, it's like I said about Cleveland House. Okay, massive changes. You can't use old flood data to estimate anything. You have to use the rainfall data and use a model to convert that rainfall into what the flood level should look like corresponding to a design storm. And that is what we do in the design storm approach. The design storm approach is the basis for all urban stormwater design across the world. So essentially, most of you guys, when you're using hydrology, you would be doing urban stormwater design. That would be based on the design storm estimation. If you're involved in freeway construction, road construction, you might be using regional flood frequency analysis or flood frequency analysis. Okay. In some cases, when nothing is available, rainfall will have to be used. But in most cases, you would be using flood frequency analysis or regional flood frequency analysis. So this is countrysides, big, long freeways, going into the Northern Territory type of stuff. But the moment that freeway starts entering Sydney, forget flood frequency analysis. Everything is changed in Sydney. You can't use old flood data. You have to use the design storm. Okay, break for 10 minutes. And then I get back to it. And please, any comments, please jot them in here and I'll address them. Okay. Okay, folks, I'll start again. I have a question from Miguel on clarifications between the design storm, FFA, and RFFA, regional frequency analysis. I will be coming back to this again later on, but let me clarify while it is fresh in all of our minds. So our aim is to estimate QY, okay? That is our aim. QY can be estimated directly from flood data, okay? So option 1, using at site flood data, okay? You use something called flood frequency analysis. So that means you have a catchment. So let me just make up a catchment. This is your river. Okay, you're trying to build a parking lot over here. You need an estimate over here, and you have been measuring floods for some reason at this point. If you have measurements over here, you would use flood frequency analysis. That is the ideal approach. If we have flood data, use flood data in most situations. Unfortunately, the problem is flood data is rarely available where you're trying to build your parking lot or where you're trying to build a new city. So you can't often use it. Okay, you would like to use it, but it's very difficult to use it. So then the second option comes along. Use flood data from nearby catchments. Okay, and this is what regional flood frequency analysis is. Now, regional flood frequency analysis is not like blindly using flood data from anywhere in that region, but you have to take into account the difference in the catchment areas. Okay, so you have to convert for the same catchment area, the same slope, the same intensities, etc., etc. There is a little bit of a uncertainty involved in that whole process, and that is called RFFA. Okay, this one is called FFA, flood frequency analysis. So both of them are using flood data. Rainfall is not touched. The sky uses rainfall IFDs plus, oops, I don't know what happened. Give me a second, guys. Keep. And then okay, still working. Good. So the third option is using rainfall IFDs plus a model. Okay, model is what? Model is a hydrologic model. So basically, you use a hydrologic model and a rainfall IFD to give you a design storm. And that is typically what you would use in an urban setting or in a place where you've had development or where you have no flood data. Okay. So Jonah has a question about clarifying what is the meaning of a 100-year flood. 100-year flood means that the rainfall, say a 100-year rainfall, can be equaled or exceeded once in 100 years. Okay, that is what it means. It doesn't mean that the rainfall occurs once in 100 years. It can be equaled or exceeded once in 100 years. So basically, a 100-year rainfall is a very rare rainfall. Let's give you an example. I'll give you an example of a flood. It's much easier to explain than rainfall. But suppose this is your flood time series. Okay, so your yearly data is like this. Okay, now annual maximum value you're having is small over here, 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 etc. Okay, now the highest value, the maximum value, is equaled or exceeded only once in your entire record. So suppose this is 20 years long. So this is your 20-year empirical flood estimate. Okay. But the second highest value is equaled or exceeded on average once in 10 years. Okay. So basically, it all comes down to what is the frequency with which that particular rainfall or flood value can be equaled or exceeded. And that is what we mean by the average recurrence interval. This point will become clearer as we go into the applications because, I mean, this is what we use for all of the design flood cases. Okay, so what are we trying to do? We are trying to develop IFTs. Okay, what are IFTs? They are intensity, frequency, duration relationships. So we need data on rainfall. Okay, because the whole idea is that we need annual maximum rainfall. And if we have lots of these annual maximum rainfall data, they are what will give us our design rainfall estimate. So how do we get this data? Well, the data comes from our rain gauge network. So this is Australian gauging network that has been used in ARR 2016. Okay, and this is actually a streamflow network, which is being used in RFFFA or flood frequency analysis. So this is what has formed the basis of our streamflow estimation, design flood estimation in Australia. And the rainfall information that you have over here is what is used for giving you the IFT relationships for each latitude, longitude in Australia. So how do we go about doing it? Well, a design storm is what we have discussed. It's a hypothetical storm. You use this as the input into a model that represents your catchment. And then the output that comes over here is called a design flood hydrograph. Okay, so if you think about it, it will increase to something like this. And then this value is your design flood. What is the design storm? Design storm will be something like this. Okay, until a duration D. So this is a D duration design storm. Okay, and this design storm is used as an input into a model and finally gives you a hydrograph. This hydrograph is a plot of flow versus time, and its peak value, its highest value, will be the corresponding design flood. So if this storm is your 100-year storm, then the peak value will be Q100. That is the whole idea. Okay. Don't worry, I'll come back to this again. These are tricky concepts, and I understand that they might be creating a little bit of confusion. So what is this design storm approach all about? Well, At the end of the day, we need QY. That's what we are after. Okay? So we are after a design flood. So what do? We need to have our design storm. From this design storm, we subtract losses, okay? And this is called the design excess rainfall, which becomes an input into the model. And then finally, this model gives you a hydrograph, okay, with this peak value being QY. That is the idea. Now, how do you get this design storm? And what does this design storm look like? Well, the design storm will look like this. It won't be a constant value. It will look like this with P on the y-axis and T over here. And the length of time over here will be D, which is your duration. Okay? So how do we get to this level? Well, what we do is from our rainfall data, which is our IFD, okay, we first decide the probability. Is it a 100-year flood? What is the Y over here? Okay. Then we decide the duration D. Do we need a 10-hour duration storm or a 3-hour duration storm? And there is a very good basis for selecting the length of the storm, the duration of the storm. I'll come to that later. Okay. So now, once you have all of this, then you have YID. That is how it is written. YID, okay, which is the design intensity, which is I, intensity for a AEP or ARI of Y and a duration of D. Okay, so this value might be, say, 60 millimeters per hour. That is your design intensity. Now, this design intensity goes on for duration D. So next thing you want to do is you don't want it to be constant, because right now, if you think about it, it is just this constant line that you're having that is finishing at duration D. But a real storm does not look like this constant line. It has some pattern about it. So what you do is you apply something known as a temporal pattern, and then you have a real design storm. A design storm that is not constant, has an average intensity of YID that you had over here, but it actually changes in time. It has got some temporal variability. This is what is the basis for estimating the final design flood. I've covered a lot of concepts here, guys, but this is kind of important to understand, okay? It's all starting with the IFD. But the IFD is of no use until you know your Y, until you know your D. Okay, once you know all of this, you have this intensity. That is what we are going with. But this intensity is not realistic. It needs to change with time. So you have to have this pattern, this temporal pattern. Now, this starts looking like a storm, like a real design storm. Now, this design storm then goes into a model. What does the model need? Model needs some basis of estimating losses. Okay, losses in this case will mostly be infiltration. Okay, and some basis of converting it to a hydrograph, which is over here. And the peak value from the hydrograph is the flood that you're after. So this, in essence, is what? a design storm approach looks like. Okay. Now, let me go ahead and tell you how it goes about. So I've already discussed what is IFT. Let's move on with this. This is an example IFT relationship. So what do we have over here? So look at the y-axis. So this y-axis is I. Yeah, difficult for me to write like this, but this is I. Okay, this is going up. That's on the y-axis. What do we have on the x-axis? That's duration d. What do we have here? These lines that you're having are y or 1 upon y. Okay. So when I say y or 1 upon y, I mean like 100-year storm. And 1 upon y, 1 upon 100 is like a 1% AEP. These are two interchangeable terms. If you know one, you automatically know the other. So basically, you're having these different lines that designate whether it's a 100-year recurrence or a 1-year recurrence interval. Okay. Now, suppose you're interested in intensity for say 12 hours. Okay. So you go up 12 hours. Now, you know your structure is a very risk-averse structure, and you need to design with a probability of failure of 1 in 50. So you basically look for a 50-year ARI, okay, which is this guy. And then you stretch it across. That's your intensity. So this is essentially 50 I 12. That is your design rainfall. The same plot can also be plotted in terms of depth. So this is millimeters per hour. Okay. This guy is just millimeters. So what they have done is they have integrated the lines on the left-hand side and you have the depth. Because many a times what people need is the depth. And this depth is what they are working with. Okay. So this is exactly the same two terms. This right-hand side fellow is just an integral. It is just converting the left-hand side plot into depth units. Where do you get them? Well, you get them from a website, and I'll show you the website. I have it over here. This is the website. So this website that you have, look at the website address, okay, bom.gov.au/water/design rainfalls, blah, blah, blah. Okay, this is giving you the 2016 design rainfalls from ARNR. In order to estimate them, you can estimate it for a single point by providing the latitude or longitude, or probably the easier thing to do is just look at a map. Okay, so if I look into a map, then sorry, it's having some problem in terms of map interface, but typically you would have, okay, so you can't really specify on the map, you have to know the latitude and longitude. So if we roughly say latitude of say 26 degrees and longitude of 155, okay, and then we just submit this thing. It might give you an error, but that is the general idea. you should be in a position to estimate for this latitude and longitude the resulting IFT. Okay, so you have to specify the latitude, longitude in a certain format, and once you have followed the format, you will have a plot that will look very similar to this plot that you're having over here. So that is basically what your IFD system looks like. And that is what you have to use in your problems, because you'll be having a second assignment that is trying to estimate the floods, and you'll be having tutorial problems that will be using this IFD website as the basis of estimating the flood values. Okay. I'm going to skip all of this. I've already told you what it is. I told you about these Australian rainfall and runoffs. These are documents that were developed before in paper terms, but the most recent version is available over the internet as a document. And this is a very powerful document. It has a lot of good guidelines as to how you should estimate a design flood in different situations. Okay, so basically, if we skip the history, what has been used to estimate the IFDs is this information. Okay, we have used this information, which is the network of rain gauge stations, so this rain gauge station were used before in the previous version of ARNR, but nowadays we have increased it very significantly. The number of long-term stations has increased fairly significantly for the case of the 2016 ARNR. And the more data you have a better way of being able to estimate the IFT. Okay. Now, I've told you where to get the IFT information from. I think what is more important is to understand, especially in a graduate course, how these IFTs are specified in the first place. So basically, what happens is, if you take a time series, in this case, it could be the rainfall time series with time, okay? These could be the time series. So this might be measured at a single gauge. Well, idea is that you can just take the annual maximum values of this time series. Okay. And once you take these annual maximum values and you just express them in probability terms, that means the highest value over here is this guy, okay, which has the lowest probability of being exceeded, while the lowest value, which is over here, is most likely of this guy. Then what you're having is you're having a relationship of the annual maximum rainfall against probability. And what you can then do is you can then fit a probability model, okay? And then from this probability model, you will be estimating some parameters, okay? And then finally, you can use the model to extrapolate or interpolate. What does this mean? Well, How many values do I have over here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, roughly 20 values. Okay? Now, if I just have 20 values, that means I have 20 years of data, then I don't know just from these 20 years of data as to which would be the rainfall that will be equal or exceeded once in 100 years, because I just have 20 years of data. So I just have 20 data points. I need at least 100 years of data to be able to estimate the 100-year rainfall with any type of certainty, which I don't have. So what do? I take my 20 years of annual maximum rainfall, and then I fit a probability model. What is a probability model? Well, a probability model is essentially trying to find out the intensity that you need for a given exceedance probability. The exceedance probability for the highest value over here, okay, the highest value has the lowest exceedance probability. If I have 20 values, the exceedance probability of this guy is roughly 1 upon 20. The chances it will be exceeded in 1 upon 20. The chances this guy will be exceeded is roughly 1 on 1. Almost all the time, this guy will be exceeded because this was the lowest value on record. Now, I essentially use this relationship, use this information to fit a probability model that requires specifying some parameters, and the probability model will be essentially having a probability distribution. Okay. And then once I have a model, it's very simple. All I have to do is to plug in a new probability, maybe 0.001. Okay. If it is 0.001, that exceedance probability is for a 1 in 1,000 year estimate, or 0.01 for a 100-year estimate. And then for this new probability, I can estimate the new value of my intensity and use it for the design applications. So this is how intensity frequency relationships are developed. You collect the annual maximum value, then you fit a probability model, and then use the model to estimate the design intensity for any given probability. You don't have to do this thing. There is no assignment, etc. on this particular step, but it is important to understand how roughly these type of things happen. So how do we estimate this probability model? Well, we have certain procedures for estimating design rainfalls up to infrequent events, which are dealt through the IFD curves. Okay? Then when you start looking at really extreme events, like the events that you would need to design a flood spillway, then you start looking at something called a probable maximum precipitation, or PMP procedure. Okay, I know that I'm covering a lot of ground over here, but there is a different design procedure for the most common IFD problems that we are interested in. And these are the IFD problems that are typically for urban stormwater modeling. So basically, for these urban stormwater problems, we use the Bureau IFD procedure. But if you're interested in very infrequent, very rare, and extreme events, a separate procedure is used called the probable maximum precipitation procedure. And I will discuss that later on. Okay. So what probability model to use? Well, there are certain probability models that have been developed by hydrologists across the world. Okay, the one that is used in Australia, it's called the Generalized Extreme Value, or GEV probability model. Okay, I won't get into details, but for all practical purposes, what this is a probability distribution. And this probability distribution has been mathematically derived because it is very well suited to characterize maximum events. Maximum events because we are looking at the annual maximum rainfall over here, or the annual maximum flood. So your flood is a regular random variable, but when you consider the highest of these floods, then that is a different type of a random variable that is better characterized by a GEV distribution. Now, you would have used probability distributions like the normal distribution or the Gaussian distribution for constructing confidence limits or performing hypothesis tests in regression modeling. Okay, that is something that would be used for normal, regular type of variables. When you're looking at an extreme variable, a variable that is a maximum of a lot of variables, then special distributions are used. And this is what is referred to on this slide. Okay, so in Australia, they use the GEV model as the basis of fitting your flood and intensity, frequency, duration, probability models. And I will discuss this later on, but when you have flood frequency analysis, you need to estimate parameters. Okay, so these parameters of the probability models can be estimated in a number of different ways. The most common way that is adopted nowadays, especially for flood frequency analysis, is to use something called the L moment approach. I won't not getting into details, but this is a way of estimating parameters. So basically, estimating parameters is like trying a bunch of different parameters out and seeing for that parameter what is the fitted flood frequency curve. Now, in some cases, when you use a certain parameter, like this one, if I use really bad parameters, my flood curve might be over here. Then I know this is a bad curve, okay? Or my flood curve might be over here. I know this is a bad curve because my actual data is sitting over here. So you will keep on iterating using these approaches, different parameter values, until you get a very good line of best fit. Okay, and the procedures that are used in estimating these parameters is what I'm referring to. The method that is used for that, especially for floods, is called L moment analysis. Okay, so I will skip the ARNR 87 procedure because that is out of date now, and we are now using ARR 2016. This is only here for reference. You can have a look at your notes and the PowerPoints to try to estimate. In ARNR 87, the probability distribution was different. It was a log normal or a log Pearson type 3 probability distribution. Now we are using a GEV distribution. So I'll skip the stuff on the ARNR 87. But for ARNR 2016, I showed you the website, and essentially what you have to do is, if I had my browser set up properly, you would have seen a map over here. And then from the map, you can either click at a point or specify its latitude, longitude. And when you do this thing, you will get as an output either a table, which is what? Which is duration running down, AP running across, and units of millimeters, meaning depth, design rainfall depth over here. Okay. So this is basically what is the output that will come out from the system. If you are interested in very frequent rainfalls, you tick a button over here, okay? And then you're having sub 1 year ARI rainfall. So what is this? This is 12 events per year, 1 event per year, 4 events per year, okay? So this type of information, 12 events per year, might be needed to design, say, a rainwater tank or a roof drainage structure, okay? Not for a flood event, but for a small rainwater tank or a roof drainage structure that is now becoming increasingly a part of our livelihood. Remember your evaporation calculations that we discussed last week. We were talking about the frequency of irrigation. So maybe that frequency of irrigation is something that is linked to these type of estimates. You can kind of gauge what is the typically weekly highest intensity that you might be having in, say, an irrigation system. And that might allow you to set up your crop planting patterns, etc., etc. Okay. Now, this last option that you have is when you click on this is the rare design rainfalls. And these rare design rainfalls allow you to extrapolate. So typically IFT will be up till here, 1 in 100. But if you want to go to the rare design rainfalls, it allows you to extrapolate up to 1 in 2000 rainfall, 1 in 2000 year rainfall, which is still not your probable maximum precipitation. Then beyond it, you will have very rare to extreme rain, which is what PMPs are all about. Okay? Okay. What do you get? You get either a table or a chart. This is an example of a chart. This is typically what you would have. So this is your intensity in millimeters per hour, and this is your depth, okay, in millimeters. So basically the same information, but presented in two different forms. The main thing to remember is if it is given to you, you need to know the duration that you're interested in and which curve you want to go for, and then you're able to estimate the corresponding design intensity. Okay. So this is just showing you an illustration of the website that I showed you before. In this website, there have been a lot of changes made beyond what was available in ARNR 87. But again, this is not really relevant for you because you're just using ARNR 2016. So I'll skip this part. I'll skip this part also because this is how the IFT parameters and curves have been developed in the first place. But essentially, once you use these intensities, you are in a position to estimate your YID, okay, for any latitude, longitude in Australia. So this is the IFD information that we use to estimate our design storm. Now, I understand I've covered a lot of ground, but I'll just try to recap. Yep, I have a question over here. Good. How is the duration chosen? I'll come to that in just a minute. But I'll just recap this entire thing. We are after a design storm. Okay, that's what we want. What should the storm look like? It should look like this: P versus time. Okay, up till some duration D. Okay, and its average value should be something which basically has, say, a value that I'll just call P bar. Now, what we do in order to get here is step one, use IFD. Step two, specify Y and D. Okay. And step three, estimate YID. And then P bar is essentially equivalent to YID in units of mm per hour. Okay. So once you have this thing, you can estimate the depth, which is equal to YID multiplied by D. So that is the total depth of rainfall in millimeters. And then finally, you get the temporal pattern. And this temporal pattern is what makes it look like this. So if this makes sense, let me take a question. Number one, which Y to use? Okay. So this Y, which is the ARI or AEP, will be given by the council or guidelines. So the Y that you have over here, which is the recurrence interval, that is specified to you by the council or by some road design guidelines or rooftop design guidelines or some type of guidelines. And what are these guidelines trying to do? They are trying to balance the risk associated with the structure you're designing. If you're designing a dam spillway, you can't allow the dam to fail, because if the dam fails, in the case of Sydney, you stand to potentially kill 500,000 people. So you cannot design a structure that allows for this type of a failure. So you will have the design guidelines by a body that is called as the ANCOLD, which is the Australian National Commission on Large Dams. And ANCOLD will say that for Warragamba Dam, use Y is equal to 10,000 years. Okay? Council might say for a little stormwater drain, use Y is equal to 5 years or 2 years, depending on specifications. That comes from the council or from guidelines. So that is one choice. Second thing is which duration to use. Okay, so this duration is a function of catchment size. If you have a small catchment, you just need rainfall for, in some cases, just 10 minutes for a flood to happen. So unfortunately, we are in a lockdown. So many of you might not have been to UNSW. But some of you who have been to UNSW would know that there is a upper part of UNSW which is towards the coastline, okay, which is adjoining Botany Street, and the lower part of UNSW is adjoining Anzac Parade. Well, if it has been raining for 7 minutes at UNSW, you will see the stormwater drain on Anzac Parade flood. This is typically what happens because the catchment area for UNSW is barely 1.5 to 2 square kilometers. Okay? So you just need 7 minutes of rain for there to be so much water that the pipes at the bottom of the catchment cannot contain it all, and they will tend to spill, and you will have some water coming onto the footpaths, coming onto the road. Okay, our students get splattered by water whenever there is rainfall because the car keeps moving, and of course there is water on the road, and the poor students get drenched. This is all poor stormwater design. The stormwater pipes at the Anzac Parade end of UNSW are not as big as they should have been. But again, that is besides the point. The point over here is it just requires 7 minutes of rain for that flood to happen. And that is a flood. That flood is not killing anyone, but it is a flood because the water is not contained by the pipe. It is a failure of the functioning of the pipe. So it is a flood. Okay? So you're having a failure of the system in that situation. And that flood is occurring because of a 7-minute duration rainfall event. Now, a 7-minute rainfall in a Murray-Darling basin would not create a millimeter of difference on the flow level at the outlet of that catchment. 7 minutes is way too short. So the duration of the rainfall that you need to choose is very much a function of the catchment size. Small catchment, short duration, large catchment, big duration. That is the general rule that is adopted. Specifically what you have, I'll come back to that later on. Okay. Now, we have understood how you estimate the design rainfall. Okay, I mean, the concept is tricky, and I've covered a lot of buzzwords. I've talked about generalized extreme value distributions, okay, extreme events, probable maximum precipitations, things like parameter estimation, L moments that I don't think many of you will be understanding, but that's fine. Don't worry about it. But at the end of it, you know how to estimate the design rainfall for any latitude, longitude in Australia. Okay. There is a problem. Just like you need a temporal pattern, you need to vary the rainfall in time. You also need to vary the rainfall in space, because rainfall is not a constant depth across the catchment. Across the Murray-Darling Basin, you would not have the same rainfall everywhere in the basin. There will be spatial variations. Just like you have a temporal pattern, there is a spatial pattern. And basically, to account for spatial variations, you create what is known as aerial reduction factors or ARFs. Okay, so when do you use an ARF? Well, a ARF is essentially a factor that is saying that the rainfall that falls at one point, so this is our catchment, okay? So rainfall over here will be higher than the rainfall which is an average over the entire catchment. Why? Because in this catchment, some points will have a very high rainfall, some points will have a very low rainfall. When you average the whole thing out, the extreme rainfall that you have across the whole catchment is likely to be lesser than the extreme rainfalls you have at individual points. So basically, when you look at what the rainfall should be as an average across the catchment, you need to multiply with an ARF. Okay, so when you need to use an ARF is when you need design rainfall across entire catchment. Okay. Now this ARF is very close to 1. It's not very different than 1, guys. So don't be worried about it. But basically, when you have very big catchments like 1,000 square kilometers or 10,000 square kilometers, its value can be reduced by as much as 30%. So in typical urban settings where you're doing urban stormwater design, you would not have, catchment areas that are more than 1 square kilometer. So most of the time the ARF will be exactly 1. But suppose you have to estimate the design rainfall over, say, the Warragamba Dam or the Hume Dam or some big dam which has a big catchment area. Warragamba Dam catchment area is 10,000 square kilometers. Okay, you can't just use the IFD curve for the spillway of Warragamba Dam to estimate the design rainfall. You take that IFD curve, once you have the intensity, you then multiply it with this factor. And the factor will be about 0.7, 0.75, 0.8, whatever it is. That becomes the average rainfall that goes into your rainfall runoff model. And the rainfall runoff model is what you would then use to estimate the design flood. Okay? So basically, think about it again. We have discussed design storm. Design storm is coming from the IFD curves. But IFD curves is for one point. You just supplied as an input the latitude and the longitude. Sometimes you need the design storm, but for a big area, not one point. Okay? And this is especially important when you have a big catchment, where you have big dams or spillways. So when you have a big area, and I'm talking of areas that are more than 1 kilometer square, okay? So not an urban catchment, big areas, then you should consider this aerial reduction factor as a way of converting a point rainfall to a catchment averaged design rainfall estimate. Okay. Now, I have mentioned that IFT is constant in time, but we need to vary it in time. We need a temporal distribution. And this temporal distribution could be like this, which is a constant in time. But if you use this guy as an input into your flood model, as compared to this fellow or this fellow, the flood will be very different. So if your input is this, the flood might be higher. If your input is this, the flood might be lower. So what temporal patterns should you be using? Well, just like you use the annual maximum rain to estimate the, just as you use the annual maximum rain to say estimate your IFD relationships, okay? The same way you figure out what are the time variations of those annual maximum rains. And then based on those time variations, you form these design temporal pattern. So what is the temporal pattern? Temporal pattern would typically be specified. I'm skipping the ARNR 87 stuff. That is not important here. For 2016, you would have different temporal patterns for different areas. And essentially, this is what you would have. You will have an ensemble of temporal patterns. Okay, so typically 10 of them. So in this case, you have a duration of say 12 hours. And for these 12 hours, you are having one temporal pattern over here, okay? Another one over here. All of them add up to 100% because all you are having over here is a percentage of the total rainfall depth for each hour being specified on this temporal pattern. So these temporal patterns are available across 12 regions in Australia, okay, and multiple sub-regions in Australia. But essentially, at the end of the day, what you need to do is, if you look at ARNR for your latitude, longitude, you would have a link to be able to get 10 temporal patterns for your duration. And once you have these 10 temporal patterns, you can create 10 design storms. Okay, so you don't have one design storm, you're having 10 design storms because you can have 10 different temporal patterns. Now, once you have these 10 design storms, then you can have 10 flood hydrographs, okay, and then 10 estimates of QY. Okay, so you have 10 different answers that you are interested in for the design flood, and your final estimate is an average of these guys. Now, again, I have covered a lot of information over here. I'll try to recap it, and I know that you're confused, so just bear with me, okay? What are we trying to do? We're trying to estimate the design flood. The design flood occurs, say, once in 100 years. We don't have flood data. So what do we have? We have rainfall data. From this rainfall data, somebody has cooked up these IFDs, which are sitting on this website. So this website is where you go, you specify the latitude, longitude of this location. And then once you have this latitude, longitude, you get the intensity, frequency, duration diagram. Okay. Now, you know how big your catchment is. There is some rule that you can follow. I haven't discussed that yet, but I'll discuss that very soon. That allows you to guess what should be the duration. So we know the duration. You've looked at the council guidelines that tells you what is the design AEP. Okay, so you know your Y, you know your D. Now you go to the IFD diagram, you get the design intensity for your duration. This is something in millimeters per hour. Okay, you can convert it to a depth by multiplying the millimeters per hour by the number of hours, which is your duration. Now you set, you know this is the rainfall that came and hit your catchment, and your job is to estimate the corresponding flood. Okay? Now, how do you go about estimating the flood? Well, the first thing you do is, you know your rainfall will not be constant for those number of hours that you have assumed the duration to be. Okay? It will vary in time. So you have to convert your rainfall to a temporally varying design storm. How do you do it? You again go to ARNR 2016, put in your latitude and longitude, and you can download the ensemble of temporal patterns. What are these temporal patterns? That's what it looks like. There are 10 patterns. Each one of them will add up to 100%, because all they are telling you is what percent of the rainfall happens in the first hour, second hour, third hour, fourth hour, 12th hour. Okay? And once you have this thing, you can create your temporal patterns. Once you have your temporal patterns, there are typically 10 patterns given to you. You can then use these as inputs 10 times. And each time you use it as input into your model, you will end up with a different answer. So you'll get 10 flood hydrographs. The highest value of the flood hydrograph is the QY. You'll get 10 estimates of QY. Okay. Now you might be thinking, why in the world do I want 10 estimates of QY? I just want one design flood. Well, the reason you get 10 estimates of QY is because there is uncertainty in getting one estimate. So the best way to estimate your QY is to then take an average of these 10 QYs. And that gives you your design flood. That is the procedure that is recommended for use in ARNR 2016. Until before this, when ARNR 87 was used, we just had one temporal pattern. And this was considered to be one of the biggest problems in design flood estimation. Because if one person used a temporal pattern associated with a slightly different latitude and longitude, they could get a very different design flood than another person with a slightly different latitude and longitude. So you can imagine legally it used to create so many problems for councils, because suddenly people could end up developing these, high-rise apartment blocks or new developments with completely inadequate stormwater structures, just by shopping around which temporal pattern would allow them to put in a thinner pipe, so that they can pass the buck onto the poor residents who then have to suffer with the flooding that follows year after year, while they're living over there. So this is the reason why we use an ensemble of temporal patterns to reduce the uncertainty that is associated. Now, I have a question, and the question is about the areal reduction factors. So the areal reduction factors, ARF, okay, is only important for big catchments. Okay, it is equal to 1 when catchment area is less than 1 kilometer square. Okay, typically, even when the area is less than 100 kilometers square, this areal reduction factor is barely a 0.97 or a 0.95. It doesn't really matter. The ARFs start mattering a heck of a lot when you're looking at big catchments. Okay, big catchments are only important to you in rural settings. Okay, in far remote countryside settings, that's when ARFs become important. But to be on the safe side, you should just use the ARF whenever you're working anywhere away from the city. Even if it is a 0.97 or a 0.95, doesn't matter, just use it, okay? And it'll give you something that is, let's say, legitimized by the Australian rainfall and runoff, which is what you're after. ARNR gives you a legal, let's say, confidence behind your design. If you're doing a design that is not complying with ARNR, you can get in trouble. So in Australia, whenever we have to do hydrologic design, ARNR has to be followed. And it is for a good reason, because this is what the entire profession and industry has decided is the best, the most logical way for designing, stormwater structures or any of our hydraulic structures in this country. Okay. Okay, I'm coming to the end. It's 3:47 and I've covered a lot of information, and a lot of you might be thinking this is getting difficult. Okay, just try to reason it out. If you just tread one step at a time, it is not difficult. We are interested in a design flood. Design flood comes from a design storm. We need to figure out the design storm. Design storm is obtained from IFTs. Okay, IFTs gives you a constant rainfall, which is not logical. So we need to change it by accounting for time. That's where temporal patterns come along. Okay, IFT gives you rainfall intensity for a point. Your catchment is not a point, it's a big area. So you need an average rainfall, which is where ARFs come along. Okay, and you're putting it all together to try to come up with a design storm. Unfortunately, the temporal patterns are not very stable. So if things are not stable, what do? You try to get multiple answers, and then you take an average of them. Okay, so that is what we have done with the temporal patterns. We have formed 10 temporal patterns, or an ensemble of temporal patterns, which gives you an ensemble of design floods. And then you take an average. That is your final design flood value. Okay, sounds complicated, but if you reason it out, think it out, makes a lot of sense. Okay, now I am going to skip stuff except the example. This is an example. This is your catchment. This catchment is in the Northern Territory, and you are interested in trying to estimate a 1% flood. Okay. The rainfall runoff model is some model that is called a ROB model. You don't have to worry about what is a ROB model. It's one of many rainfall runoff models that I used. Okay. The area of this catchment is 72 kilometers square. Now, for this area, there are some guidelines that I have not discussed till now, but these guidelines give you some indication that your duration should be roughly between 60 minutes to 1 day. Okay. Now, if you know that this is your duration, what do? Well, what you do is you estimate your intensity for a duration of 60 minutes, 120 minutes, 180 minutes, all the way down to 1 day. So you form a lot of design storms because you don't know what the perfect duration should be. For each of these cases, you have 10 patterns. Okay. Luckily, our catchment is 72 square kilometers, so ARFs are not so critical. Okay. And you then estimate the corresponding design flood. Now, this is what we end up getting. We get design floods which assume a maximum for a duration of 180 minutes and 270 minutes. So most likely our design duration is one of these two. Okay. And I am after the highest design flood. The highest design flood is for this guy, because this fellow, it varies a lot. When you take an average, the average would be lower. The average over here would be higher. So if I have to choose based on these plots, I would say my design duration is 180 minutes and my design is this guy. Okay, that is what we need to do in any design flood estimation problem. I'm at 3:52. I just have 3 minutes to go, but I'll just keep on going. If you have any questions, please put it in the comment or put it in the discussion board so we can discuss it later. Okay. Now, this is what happens. These are the different temporal patterns, and from the temporal patterns, we are getting different storms. So this is the durations that you're having. Okay, and these are temporal patterns. Okay, we're getting 10 temporal patterns. And from these 10 temporal patterns, we are able to create these patterns as inputs into the flood model, which then gives us our corresponding design flood estimate. Okay, now we'll skip this. This is not so relevant. The very frequent design storms or design durations are when you have 12 events per year. It's typically needed for ecological design or for rainwater tank design. It is not needed for flood estimation, but the logic is pretty much the same. Okay, skip that. The rare design rainfalls, which is where you are getting to 1% and even more rare type of flood events, are needed typically for spillways. Okay, but what we need to do for the very rare rainfall events is over here is to use procedures for estimating the PMPs, which are the probable maximum precipitations. Okay, and these, when converted to floods, give you what are known as PMFs, or probable maximum floods. These probable maximum floods are the basis for designing the spillway capacity of all of our major dams. For instance, the Three Gorges Dam would have been designed, the spillway would have been designed based on a PMP routed through a flood model, estimated into a flood hydrograph whose biggest value would be the PMF. Okay, so that is how you design for very extreme events. Very extreme events are not once in a lifetime. They are once in 10,000 to 100,000 years. So they are very, very rare events. And they are only used for really critical or really dangerous structures. Okay. One of the biggest problems the world is right now facing is whether climate change might be increasing our PMPs. Because if climate change is increasing PMPs, then that means that all the dams across the world are unsafe. That is a project that we are working on right now. I have a couple of students who are doing PhDs in this general area of work, but this is a very critical problem because that increase in the moisture holding capacity, because of which the design rainfalls are increasing, okay, that should theoretically apply to PMPs also. And that whole thing about soils getting dry does not apply for PMFs, because we are talking of a once in a 10,000 year event. If you're looking at such an extreme event, the soils are completely saturated. You can't assume them to be dry. Okay, and it creates a bit of a problem. With that, I will come to a stop. I haven't finished all the slides. I will be discussing how to estimate the PMPs in the Australian context, but please go through these notes. Please go through the ARNR IFT website. Okay, look at your tutorial questions and try to familiarize yourself with that, because the Next assignment that you would be working on, it is all related to floods, where you need to be kind of on top of all of these procedures. And please use the discussion board. So if you use the discussion board, you put questions, you can be assured that I will reply before the end of the week. Okay, guys, off to your tutorial. So there is an online Blackboard tutorial for any of you who are not attending in Webster. You can post questions and the recordings will be available through Blackboard, just like the recordings for this lecture. Okay, see you guys.